All right, so we're going to go ahead and start our discussion of column distillation, and this video will be a little bit of an introduction to how we get to distillation from last time when we talked about flash processes. We'll work through a couple of what we call cascade examples that lead us toward this whole idea that coming up with an isobaric distillation column is the way we want to go in terms of doing some of these large-scale VLE separations for many different applications. Distillation has been the backbone of the petrochemical industry for decades now. It's at the core of most petrochemical processing plants. It remains a technology that is widely used today and that companies need to use and need to employ people to operate. You'll get a chance to learn a little bit more firsthand about distillation in the third year lab. We have a big glass distillation column that's shown in the picture here on the right that is used to separate methanol and water. And then, of course, anyone who's driven past a chemical plant is used to seeing the big, tall, skinny towers. Those are often distillation columns, maybe a little bit like the one shown here on the left. So distillation is sort of our second application in terms of thinking about the equilibrium stage concept that we've been working on. We've already talked about flash processes, and we've talked about the situation where we can use flash processes to do at least some element of separation. But today we're gonna talk a little bit more about simple column distillation and start down a path that'll involve a few other situations where we'll talk about distillation and distillation columns as we go. So again, last time we talked about flash separations. This was the idea where we have some sort of a feed, we put it into a drum, we drop the pressure, and we have a situation where we get some sort of a flash that takes place and we get some separation, right? And so we talked about this in terms of saying, perhaps we have some sort of a feed that's described by some feed composition and some feed pressure. This is a constant temperature PXY diagram. MVC here is for more or most volatile component. If we're doing a binary separation here, then the most volatile component is often what we plot on the PXY and TXY diagrams. In any case, we can think about our feed as being some point up here, and then ultimately what we're going to do, right, is we're going to come in and we're going to decrease the pressure of that liquid feed, and we're going to bring that down into the two-phase region. And when we do that, drop the pressure to some lower pressure that we'll call P drum, and that's going to do some separation for us. And so we go from a liquid that has some composition ZF to now generating a vapor that has some composition Y, and we notice that Y is larger than ZF. So we have enriched the more volatile component in the vapor phase, and likewise it becomes somewhat depleted in the liquid phase. And so flash processes can do some separation, particularly in cases where you have this situation where you have a very large relative volatility. Basically, the wider this two-phase region is on the PXY diagram, the more separation you get. If you have a very low relative volatility, for example, or a relative volatility that's much closer to 1, you would see very little separation in the flash process. So generally speaking, flash processes can play a role in certain applications, particularly where there's a big difference in volatility, but oftentimes they're not very practical because we need to do more separation than is possible in a single stage operation like this. Additionally, we talked a little bit about this trade-off between the purity of the vapor product and how much of the vapor product you're actually going to collect in terms of a flow rate or an amount. And we said that generally, if we want to make the vapor product more pure, then we're going to make less of it, and then we still have to do something with the liquid product that we're making as well. So flash processes are useful for us in terms of thinking about what's going on here in terms of doing a VLE based separation, but they simply aren't going to be particularly useful in a number of different applications, so we need to do something else. So perhaps the next logical thing to think about doing would be to set up a cascade of flash processes. And so here we're looking at a situation where, we can take this initial flash process, right, where we're feeding things in here, and then we can think about doing additional flash processes on either side of things. So as we bring that liquid feed into the box labeled 3 here, we go through the flash process. We can take that liquid, go decrease the pressure again, go down to the box, the flash drum labeled as 4, do another flash, and so on and so forth. And so, we could think about this whole situation. On the other hand, we could think about taking the vapor, recompressing it to a liquid, and then doing another flash in the box labeled stage 2. And from the PXY diagram perspective, right, we can sketch out and think a little bit about what this might actually look like. And so let's think about a feed point up here. I'm just going to label that F to correspond to the feed on the other side of things. Again, we're going to be using Z sub F generally, or some nomenclature of Z to indicate a feed composition. And so we could take this feed and drop the pressure in stage, we're going to call stage 3 here, or the box that's given by the 3 on the left. And so we drop down, and we'll just go ahead and call this pressure P3, right? Because this is the pressure of flash drum number 3. Right, so in this case, we would do the separation, and we would get a situation where we would get X3 and Y3. Those would be the liquid and vapor products coming off of that drum number 3. And then, if we think about what we're going to do, with that liquid product, right, we could come in and we could drop the pressure again on that liquid, right? And if we did that, perhaps we'd take this liquid and we'll say we drop the pressure down to some other pressure that we'll call now P4. And that would allow us to generate additional products, we'll call those X4 and Y4, right, corresponding to the liquids and vapors that are coming off of drum number 4 here. Likewise, we could come in and take the vapor coming off of drum number 3, and we could recompress that to some extent. We do a little bit of what we're going to consider to be sort of a cyclic process here. We could come in and perhaps think about recompressing that up to some point, and then reducing that pressure to come back down to some intermediate pressure where, again, we would get some element of phase separation. And I'm going to change my arrow here a little bit, but we sort of get the idea as we look at this that this doesn't make an enormous amount of sense to compress or pressurize a liquid or a vapor back up into the liquid state just to drop the pressure again. But we're doing this here just to illustrate the broader concept that we're discussing here. So in this case, for example, we might then have a situation where now we have a pressure P2 that's corresponding to that flash drum number 2. And again, we could come off and say we have liquids X2 and Y2. And so we start to see that this idea of putting together a cascade process would allow us to basically enrich the less volatile component in the liquid phase and enrich the more volatile component in the vapor phase. In other words, the Y values are going to move to the right as you go up the cascade, and the X values are going to move to the left as you go down the cascade. But we have a lot of intermediate products here. L1, L2, V4, V5. All of these intermediate products are things that we would have to deal with at some point, and that's not particularly convenient from the standpoint of thinking about what we would actually do with all of those streams. And so, in this particular case, we get the feel that perhaps this cascade of flash processes doesn't make quite as much sense as one would like. Now, one thing that you might notice here, if we sit and stare at this for a little bit, is that the liquid product that's coming off of stage 2, so that the L2 stream here, has a composition of X2, right? And it turns out that X2, right, actually could have a composition that's pretty close to ZF, right? We sort of see here when we take Y3 or when we take the V3 vapor and compress it up and drop it back down, right? The point that we have here that we've sketched in for X2, right, comes back and gets a little bit closer to the composition of the feed, or ZF. And so in some ways, the L2 liquid coming off of stage 2 here has a composition that is somewhat close to the feed composition that's going into stage 3. So as a result, we might think, well, it could be convenient to just take that L2 stream, as well as the other intermediate streams that are problematic for us, and just connect that back into the next stage down. And so, we could do this for all of these liquid streams here, and we could see now that L2 is going from stage 2 down into stage 3. And this is based, sort of solely off this idea that we have this situation where our feed drops down in pressure, and then we're going to have some other situation here where, right, this X2 composition is somewhat close to the composition of the feed. And so we could see that this perhaps suggests that a cascade operating in a countercurrent mode might make some element of sense here, just from the fact that we're looking at the fact that the liquid product from each drum is closer to what I'm going to call Z sub j plus 1, right, or the next the feed to the next stage as we move down the particular cascade. And so this is characteristic of what we call a countercurrent mode of operation. But this is also somewhat tricky because, if we start to think about the implications of doing this, right, every time we go through compression or expansion, right, we have temperature changes. And so we have some basically heating and cooling issues associated with trying to keep this whole thing operating at constant temperature. Remember, in the case of our TXY diagram, we're sort of sketching this all out here in a constant temperature case. And so we'd have to have heat exchangers in between each one of these stages to maintain that constant temperature, and that's not necessarily trivial to do. Also, if you think about what's going on here, we'd have a situation where we're actually going to have quite a bit of material, or quite high volumes, in the middle of this cascade, because the volumes will get smaller, or the flow rates of the streams will get smaller as we go to the extreme ends of the cascade. And so that means that we're going to have a lot of volume of stuff to deal with in the middle of this cascade, which is also not particularly useful or helpful to us. So to get around that, we could think about a situation where we could perhaps try to simplify the heat transfer problem. We've been thinking about this by analogy to flash processes in the constant temperature world, where again we're in this situation where we have to, somehow sort of go through and do heat exchangers to keep the temperature constant as we move from these different flash processes up and down the cascade. So we could think about doing this with intermediate heat exchangers where we have a separate piece of equipment on each stream, as is indicated here on the left. But that's also intense from a process perspective and not necessarily something we really want to do, especially given that we have the option of using a constant pressure approach to things where now we can allow temperature to change and we can integrate the heat transfer element of things by just allowing the liquid and vapor streams to come into contact with each other in between the different stages. And so this is pushing us toward this idea of what we're going to see in terms of column distillation. Now, instead of allowing changes in pressure to drive the vapor-liquid equilibrium separation, we're going to start thinking about how things change in terms of temperature. And so we're going to see in the constant pressure process that we're going to be thinking about TXY diagrams. Remember, we use MVC as the most or more volatile component here. And we'll just sketch on in a TXY diagram. And so what we have going on here is a situation now where the temperature is going to decrease as we go from the bottom of the column up toward the top, right? And so what ends up happening is at each stage as we change the temperature, we end up with a situation where we progress more and more toward enriching progress more and more to where we're enriching the more volatile component toward the top of the column. Additionally, we're going to come in and we're going to do a boil up and a reflux into the system in order to deal with this issue of balancing the amount of volume we have in the column. So now we'll be able to circulate material through the cascade in a way that keeps us from having this situation where the volumes in the middle of the cascade are much greater than those at the ends. And that also is going to push us a little bit closer to what we'll see in a constant pressure distillation column. All right, so, if we think about this TXY diagram, right, essentially what we're saying is that we're going to do something like this, where perhaps, we start out at some higher temperature, T5, and we're going to progressively, as we go, decrease the temperature. And what we're going to see happen here, right, is as we go toward lower and lower temperatures, the vapor product that we're getting at each one of these stages becomes more and more enriched in the more volatile component. Right, we can see that pretty clearly here if we look at Y5, Y4, Y3, so on and so forth. Right, so what we're doing as we set up this constant pressure cascade is we're using temperature to drive the separation. And we're going to get the more volatile component toward the top of the column, and we're going to get the less volatile component in the liquid phase down toward the bottom of the column, right? Because the liquid phase compositions move in the opposite direction, and the liquids are moving down, so they're taking the less volatile component with them to ultimately enrich toward the bottom. And this is going to be the principle behind how we do column distillation for vapor-liquid equilibrium-based separations. Now, we take this system, and instead of having different blocks like we have here, we're going to take this cascade and put it ultimately into a column. We're going to think about columns that contain trays for right now. Eventually, we'll talk about a different approach using what's called packing materials. But the idea here is that each tray in the distillation column acts as one of those boxes, right? And so each tray or each stage is going to facilitate the mixing of liquid and vapor and allow those liquid and vapors to come toward equilibrium. In our equilibrium staged concept that we're considering here in our course, we're going to assume that they actually do reach equilibrium, but in reality, right, we're approaching equilibrium at each stage as we go. And as you can see here over on the right-hand side, basically the vapor and liquid mix on each stage, and then the liquid separates from the vapor and moves down to the next stage while the vapor rises up. And at each stage, as we move up the column, the temperature gets lower and the more volatile component becomes enriched in the vapor phase. Ultimately, we're going to take that vapor product out the top of the column, right? We're going to condense that down, and then we're going to take that product off as a distillate product. And we'll reflux some of that liquid back in the column again to keep things balanced within the column. At the bottom of the column, the less volatile component is being enriched. We have a liquid that comes out the bottom of the column. That's going to be partially re-vaporized. That vapor will be re-injected into the column, and we'll take off the bottom's product, which will be enriched in the less volatile component. We're going to talk a little bit more in class about column internals and sort of the structure of distillation columns, but we want to start getting in mind this picture of how distillation columns operate and how they're connected or sort of can evolve from the idea of doing flash-based separations where things are perhaps being done isothermally to one where now we're going to run an isobaric distillation process and use temperature differences to drive the VLE-based separation of components. So we'll go ahead and wrap things up here, and we'll continue in class talking a little bit more about column distillation.